Hello and welcome to the 11th tutorial of module database 2. This module is intended for both departments MET and business informatics. Before going deep into practice, let's summarize today's lecture first. Back again to the internal architecture of our database management system, which represents a map of our topics that we are learning during this course. During the previous week, we learned about the log manager and the recovery manager. Today, we will investigate how the transaction manager works in detail. Okay. Now, as illustrated in this figure, the transaction manager is responsible for planning how many transactions will be executed simultaneously at the same time in parallel. We can consider the scheduler as the brain of the transaction manager. Without the scheduler, the database will execute all transactions sequentially, which will take a lot of time. Okay, the perfect scenario is the serial schedule, which reflects executing the transaction in sequential order. We know that this schedule is time consuming. However, we can use it to test if our schedule that consists of swapping between transactions to execute them in parallel is good enough or not. Here is an example of executing two transactions, T1 and T2, in parallel by swapping them on the CPU, Central Processing Unit. This is called concurrency, which is a concept that is a part of every operating system, which allows many applications to run in parallel at the same time. For example, your computer is running an Excel sheet, Firefox web browser, Google Chrome web browser, and media player at the same time. How it does so? Well, using concurrency. The main idea behind swapping between transactions is to identify conflicting steps that, if we swap them, will cause a problem, and non-conflicting steps that swapping them will not affect at all. We will use these notations to read the sequence of steps that belongs to a specific transactions and to represent these steps. Okay, the first notation, which means that transaction T is reading element X. The second one means that transaction T writes X. Okay, now let's see the three types of non-conflicting steps. The first one is two transactions read different elements. Okay. The second one is two transactions read and write different elements. The third one is two different transactions that write different database elements at the same time. Okay. Transaction I and the transaction J. Okay, let's learn about the three types of conflicting steps. The first one is to action of the same transactions. Read and write for transaction I on different elements. The second one is two transactions that write the same database element. This will cause a problem. The third one is two transactions read and write the same database element. So transaction I and J tries to write database element X, both of them. So these three actions are conflicting. Executing them will cause a problem. Okay. To check if a certain sequence of steps for a group of transactions is non-conflicting or not, we have to draw a graph for these transactions based on the given steps and check if this graph contains a cycle or not. Before figuring out how this works, let's revisit the concept of graph. Okay, a graph is composed of a set of nodes, the purple ones, and a set of edges, the arrows, that connect between the nodes. Both the edges and nodes construct a graph. This is a directed graph, which means that all of the edges have a direction, starting from certain node going to another certain node. Okay. Again, the edges connect between nodes, and we are interested in the directed graph to check for cycles. A cycle can be found if I start from a specific node and I will end up at the same node again. So this is called a cycle. A graph that contains a cycle represents a non-serializable group of transactions that executing them will change the state of our database. This one contains no cycles. Don't be deceived easily by the edges. Okay, look carefully at the directions. This is not a cycle. And a cyclic graph is a graph which contains no cycles. The acyclic graph represents a good group of transactions that will preserve the state of our database, and executing them will cause no problem at all. Here is an example of an acyclic graph. Again, don't be deceived easily by the edges. Look carefully at the directions. Okay, in order to draw a graph for a given set of steps for a group of transactions, we have to do the following steps. First, we must write down the conflicting steps aside. We will use them to draw a graph okay. Then we will scan for these types of conflicting steps. If any of them is found, it will indicate which transactions comes first in order. Then we will draw an edge between the two transactions in the same order implied by the conflicting steps. Okay, let's see an example to fully understand these steps. Here's an example. Given the following set of steps for three transactions, R1, R2, and R3. As we said before, don't forget to write down the conflicting steps aside. Then scan for the conflicting steps. In this example, the green conflicting steps state that transaction R2 comes before transaction 3. So I will draw a node that represents transaction 2 and another node that represents transaction 3, and I will draw an edge start from R2 going to R3. Okay, so after finishing constructing the graph, we will scan the graph for cycles. We want to know if a cycle exists or not. So transaction 1 must be executed, then transaction 2, then transaction 3, and this is a directed graph, and there is no cycles. Here's another example. However, in this case, the graph contains a cycle. So this sequence of steps will cause a problem if they are going to be executed by our database management system. Okay, we can generate a conflict serializable schedule by swapping non-conflict steps. Here is an example of swapping non-conflict steps. which will result in a serializable schedule of transactions that will cause no problems and is equivalent to execute the transaction in sequential order. So it will cause no problem. Here is a full example of swapping non-conflicting steps, which will get us back to the original serial schedule of transactions. So by swapping the read of transaction 1 and write of transaction 2, then here we will swap read operation of transaction 1 and read operation of transaction 2. Next we will swap write operation of transaction 1 and write operation of transaction 2. Then we will swap the write operation for transaction 1 and read operation for transaction 2, and we end up with executing all steps of transaction 1, then all steps of transaction 2. So we end up with a sequential serial schedule. And don't forget to write down aside the non-conflicting steps if you are solving this kind of problems. Okay, let's solve the following problems together to practice how to check for a cycle inside a graph, how to construct a graph for a given set of steps for a specific group of transactions, and so on. Okay, the first problem. Let's solve the first problem. Okay, consider each of the following schedules. Draw the graph for each one and tell whether they are conflict serializable or not. So we have 4 schedules of steps for a group of transactions. Okay, transaction 1 and 2 and 3, transaction 1, 2, 3, 4, transaction 1, 2, 3, transaction 1, 2, 3. Okay, we will solve them one by one. So for each sequence of steps, we need to draw the graph and check if it contains a cycle or not. If it contains a cycle, then this sequence of steps is not conflict serializable. And if the graph contains no cycles, then this sequence of steps is conflict serializable. So let's solve the first one. Okay, as we said many times before, let's minimize it. Okay, as we said many times before, don't forget to write down the conflict steps aside before starting solving the problem. Okay, here we have a write operation on element x for transaction 1, then a write operation of element x for transaction 3, then transaction 2 writes x, then transaction 4 writes x, then transaction 4 read the value of element y, then transaction 1 write the value of y. Okay, we will scan these steps for all types of conflicting steps. So write transaction 1, write operation, write element x. We need another transaction that also writes x. So transaction 1 writes x, and transaction 3 is writing x. So transaction 1 must come before transaction 3. So we will draw a node for transaction 1 and a node for transaction 3 and an edge from T1 to T3. Okay. Also transaction 1 must come before transaction 2 because we have another write operation of element x for transaction 2. So transaction 1 must come before transaction 2. So I will draw another node for T2, and I will draw an edge starts from going from T1 to T2. Okay. Again, after the write operation for transaction 1, transaction 4 writes the element x. So transaction 1 also must come before transaction 4. So I will draw a node called T4, which represents transaction 4, and I will draw an edge going from T1 to T4. Okay. Next, a write operation for transaction 3 on element, it will write element x. So according to the conflicting steps, I will search for another write operation for another transaction that writes the same element x. So w3 of x, here is transaction 2 write x. So I have to draw an edge going from transaction 3 to transaction 2. So here is the edge going from T3 to T2. Also, there is another write operation on element x for transaction 4. So I have to draw an edge going from transaction 3 to transaction 4. So I will draw an edge starts from T3 going to T4. Okay. So we are finished with the write operation, and next the write operation for transaction 2. Okay, transaction 2 writes x. According to the conflicting steps, I'm searching for another write on variable x. Okay, and it can be found easily. So I have to draw an edge going from transaction 2 to transaction 4, and here it is. Next, the read operation of transaction 4 on element y. So according to the conflicting steps, we have two conflicting steps that start with the read operation. Okay, I have only a write operation on the same variable y. Okay, so this is type 3. So transaction 4 must come before transaction 1. So I have to draw an edge going from transaction 4 to transaction 1. So after finishing constructing the graph for these steps, actually this graph is full of cycles. Okay, I can go from T1 to T4 and back again to T1. So this is a cycle. I can go from T1 to T2, then to T4, then back again to T1, and here is another cycle. Actually, I can go from T1 to T3 to T2 to T4 to T1 again. Here is the third cycle. So this sequence of steps is or this schedule is not conflict serializable. Okay, let's solve the next one. We have a read operation for transaction 2. It will read the element D, then transaction 1 writes element E, then transaction transaction 1 reads value E, then transaction 1 writes A, then transaction 3 reads A, then transaction 2 writes C, then transaction 2 reads C, then transaction 2 writes A, then transaction 1 reads B, transaction 1 writes B, transaction 4 writes C, transaction 3 writes B. Okay. Again, don't forget to write down the conflict steps aside before starting to solve the given problem. Okay, I will scan for conflicting steps. I have read of element D. So according to these types of conflicting steps, I must find another right operation of element D. There is no right operation for element D, and there is no right operation for element E. So we will start with this right operation. Right operation of element A. So I must find another transaction that writes the same element A. Transaction 2 writes A. So transaction 1 must come first before transaction 2. So I will draw an edge between the node T1 and node T2. Here is the node T1 represents transaction 1, and here is the edge going from T1 to T2. Okay. The next one, read operation. Transaction 3 reads A. So I must find different transaction that writes the same element A, and it can be found easily. Okay, so I will draw an edge going from transaction 3 T3 going to transaction 2. So here's an edge going from T3 to T2. Also, the transaction 2 reads element C, and I can easily find that transaction 4 writes the same element C. So I will draw an edge between T2 and T4. Here's the edge going from T2 to T4. Okay. This read operation of element B, I can find another transaction that writes the same element B. So I will draw an edge going from T1 to T3. Here is the edge going from T1 to T3. Also, this write operation of element B, I can find that transaction 3 writes the same element B. So I can again draw an edge going from T1 to T3. So after finishing drawing our graph, we will check the graph and scan it to find if any cycle exists or not. Okay, don't be deceived easily. This is not a cycle. Going from T1 to T3 and going from T3 to T2, then going to T4. So this triangle, okay, represented by these 3 edges, is not a cycle. So again, don't be deceived easily. Look carefully for the directions of the edges. So this graph contains no cycles, so it is a conflict serializable schedule, and it can be executed and it will cause no problems at all. Okay, let's try to solve the next one. Okay, I have a read operation. Transaction 1 reads value x. So I must find write operation on value x. Okay, I can find it easily. Transaction 3 writes x while transaction 1 reads x. So transaction 1 must come before transaction 3. So I will draw T1 and T3, and I will draw an edge going from T1 to T3. Okay, the read operation. Transaction 2 reads the value y, and I can find another transaction 3, that writes the same element y. So transaction 2 must come before transaction 3. So I will draw an edge going from T2 to T3. Here it is. Write operation. Transaction 1 writes the element x. Okay, and I can easily find that transaction 3 writes the same element x. So I will draw an edge start going from T1 to T3. Okay, the same edge. The write operation. Transaction 3 writes the element y, and transaction 2 writes the same element y, and this is type 2 of conflicting steps. So transaction 3 must come before transaction 2. So I must draw an edge going from transaction 3 to transaction 2. Here it is. Okay, also transaction 1 reads the element y, and transaction 2 writes the same element y. So transaction 1 must come before transaction 2. So I have to draw an edge going from T1 to T2. And after finishing drawing the graph, we will scan the graph for a cycle, and we have a cycle between T2 and T3. I can start with T2 going to T3, and I can go back again from T3 to T2. So this graph contains cycle, so it is not conflict serializable, and our database management system, if it tries to execute this sequence of steps, it will change the state of our database, and it will cause a lot of problems. Okay, problem number 4. Don't forget to, again and again and again, don't forget to write the 3 types of conflicting steps aside before starting solving the problem, given the following sequence of steps for transaction 1 and 2 and 3. We will scan these steps to find the conflicting steps. Okay, transaction 2 reads element A, and transaction 1 writes element A. So transaction 2 must come before transaction 1. So I will draw T1, T2, T3, and an edge going from T2 to T1. Here it is. Transaction 1 reads element C, and transaction 3 reads element C. Okay. Also, transaction 3 reads element B, and transaction 2 writes element B. Also, transaction 1 reads element C, and transaction 3 writes element C. So our T1 must come before T3. So I will draw an edge going from T1 to T3. Here it is. And transaction 3 reads element B and transaction 2 writes element B, so transaction 3 must come before transaction 2, so we will draw an edge going from T3 to T2. Again, we will, after finishing drawing the graph, we will check if any cycle exists. Yes, I can go from T1 to T3 to T2, back again to T1. So the whole graph is a single cycle. So these steps or this schedule is not conflict serializable. Okay. Okay. Consider the following conflict serializable schedule. Transform it into its equivalent serial schedule. So given a set of steps, and the question requires that we swap the non-conflicting steps again and again until we end with the original serial schedule. So we have to scan these steps for the non-conflicting types. And here we have read operation, transaction 1 reads B and transaction 2 writes A. This is a non-conflicting steps. If we swap them, nothing happens. So we will swap these steps. Then we will scan again for non-conflicting steps. Here we can see read transaction 1 reads B and transaction 2 reads A. So these steps are non-conflicting. So if we swap them, nothing happens. Okay, swap them and scan again for non-conflicting steps. We found that transaction 1 writes B, element B, and transaction 2 writes A, different elements. Different transactions write different elements. So they are non-conflicting steps and we can swap them. Scan again for non-conflicting steps. We found that transaction 1 writes element B. Transaction 2 reads element A. So these are non-conflicting steps and we can swap them. And nothing left, and we end up with all steps and all actions of transaction 1 comes and executed before all steps and actions of transaction 2. So by swapping the non-conflicting steps, we can go back to the original schedule, the serial schedule. So after solving 5 problems, this is the end of the tutorial. But before saying goodbye, let's summarize the topics that we talked about during the course through the following figure, which represent the database management system architecture, internal architecture. So the client will write a SQL statement, and the query processor will parse and read this SQL statement, and it will try to decide the best logical plan to execute the SQL and the best physical plan to execute the SQL statement. Then the SQL will enter the transaction manager in the form of the transaction, and the transaction manager will schedule how to execute the current transactions in parallel through the scheduler. The buffer manager organizes the the data flow between the RAM, the memory, and the hard disk, the read and write operations. Okay, the log manager and the recovery manager are writing everything that is happening right now inside our database management system into the log file in order to restore the previous state of the database in case any risky or disastrous situations happen. Okay, so next time we will continue on explaining how the transaction manager works in detail. Okay, and I think the next tutorial will be the last one. I hope that you will study the lectures, you will watch the video on demand, and you will try to solve the practice assignments in home by yourselves. Okay, study well and take care of yourselves, stay safe. Okay, that's it. Goodbye.